The other operation we have is going to be the extrusion. Now, in the case of the extrusion, the compression forming process in which the work metal is going to be forced to flow through a die opening, and this will produce a desired cross-sectional shape. The process is similar to the squeezing of the toothpaste out of the toothpaste tube. In general, extrusion is used to produce a long parts of uniform cross-section because the die shape is going to be constant. Let's have two basic types. We have the direct extrusion, when we're going to push the pellet throughout the die by moving the ram against the direction. Or we have the indirect extrusion, where the die is going to be within the ram. So when we're going to force the material to be compressed within the container, it's going to be forced to leave in the opposite direction of the movement of the ram. So these are two examples for the indirect, and this one is the example for the direct types of extrusion. We can see more in the following link video. The direct extrusion, and sometimes called the forward extrusion because the specimen is going to be leave in the same direction of the movement of the ram. The starting pellet cross section usually is going to be round, but the output is going to depend on the die opening. The final cross section shape of the extrusion is going to be determined by the die opening shape. As the ram approaches the die opening, a small portion of the pellet is going to remain that cannot be forced through the die. So here, we're going to have some material that cannot be uh, pushed throughout the die. And this material is going to be called the butt. And this must be separated from the extruded section by cutting it off or just beyond the die exit. The The indirect extrusion, also called the backward extrusion or the reverse extrusion, because you can see that the extruded part is going to be moving against the direction of the ram. The limitation of the indirect extrusion are going to be imposed by, first, the lower rigidity of the hollow ram. Second, difficulty in supporting the extruded product as it's going to be exit the die. The advantage are the variety of the shape are going to be possible, especially in the hot extrusion. The limitation is that the part cross-section must be uniform throughout the length. The grain structure and the strength is going to be enhanced in the cold and the warm extrusion. Close tolerances are possible in the case of the indirect extrusion, especially in the cold extrusion. In some operations, there are going to be little or no waste material. So you can see here that we almost not going to have any butt because the ram can reach the end of the container in both cases. So the direct and the indirect extrusion process, as you can see here, once again, these are the two indirect extrusions. And the direct extrusion, we're going to have higher value for the part, while in the case of the indirect, we're going to reduce its value. The force required, or the force, or the ram pressure requirement for the direct extrusion is always going to be higher. At the beginning, then they are going to get close to each other, but still, you can see that the pressure in direct extrusion is going to be higher than the case of the indirect extrusion. Because there will be no shape change in the shape of the pellet, we are going to have a constant pressure in the case of the indirect extrusion process. For the hot and the cold extrusion. In the hot extrusion, prior heating of the pellet to above its crystallization temperature is going to be required. And this will reduce strength and increase the ductility of the metals, and this permitting more size reduction and more complex shapes to be formed. In the cold extrusion, journal is going to be used to produce adhesive parts, so we don't need to heat it up. The term impact extrusion is used to indicate the high speed of the cold extrusion process. The extrusion ratio it's also called the reduction ratio, is defined by the following equation. The reduction ratio is going to be equal to the original diameter or the original area of the pellet divided by the final diameter of the pellet. The final area of the pellet is going to be usually equal to the cross-sectional area of the die we are using for the extrusion process. The Rx is the extrusion ratio, the AO is the cross-sectional area of the starting pellet, and the AR is the final cross-sectional area of the extruded section. Remember that this value should be always more than 1, because the area of the pellet is always going to be higher than the area of the die opening. The same equation can be applied for both the direct and the indirect extrusion process. The true strain in the extrusion, given that the ideal deformation occurs with no friction and no redundant works are going to happen. So the value for the true strain is going to be equal to the length of the Rx or the length of the AO divided by the AF. Under the assumption of ideal deformation, I mean no friction and no redundant work, the pressure applied by the ram to compress the fillet throughout the die opening can be computed as following. The pressure, now once again, this is for the direct case. The pressure is going to be equal to the average flow stress. Now you can see that we have a bar above the YF. So the average flow stress multiplied by the strain, or the average flow stress multiplied by the length of the Rx. This will give us the pressure. The average flow stress can be calculated with the following equation. The K multiplied by the strain, the ideal strain or the true strain, up to power n, and divided by the 1 plus n. Okay? So the only difference between the average flow stress and the flow stress is that we divide by 1 plus n. So you can see that the extrusion die features, what we're going to have is high friction at the beginning, and then we're going to have the optimum value for the die angle alpha is going to be increasing, and then as we're going to continue increasing, the value for the higher redundant or the work at the high value of the alpha is going to be closed. So that's mean it's not about the minimum value, it's not about the maximum value, we're always going to have the optimum value for the alpha. Now, what's happening if we're going to have it as a flat? That means we're going to have some turbulences at the corners. What's happening if we're going to have it as more sloped? That means we're going to increase the contact area, and thus we're going to increase the friction forces, and thus we're going to have higher round force are going to be required. Now, various methods to calculate the true strain and the round pressure. For example, we have what we call the Johnson empirical equations. So in the Johnson empirical equation, the value for the true strain is going to be given by the following equation. True strain, or the mu x, is going to be equal to the A plus B multiplied by the length of the Rx. In the indirect extrusion, the pressure is going to be equal to the average flow stress multiplied by the mu x. In the case of the direct extrusion, the pressure is going to be equal to the y prime f, or the average flow strength multiplied by the mu x plus 2L divided by the GO. The ground force in both cases is going to be equal to the pressure multiplied by the cross-sectional area of the outlet. The power required to carry out the extrusion operation is going to be simply given by the equation that the force multiplied by the velocity of the ram is going to give you the power in watt. Now, let's have an example for the extrusion process. We need to calculate the extrusion pressure for the following example. We have a pellet that has a 75 millimeter long, and it has 25 millimeter in diameter. This to be extruded in a direct extrusion operation with the extrusion ratio value of the 4. Now this is the Rx. The extruded cross section is going to be round. The die angle alpha is equal to 90 degrees. The work metal has a strength coefficient of 415 megapascal. And the strain hardening component is equal to 0.18. Okay, now this is the K and this is the F. Now, for the Johnson formula, the A is equal to 0.8 and the B is equal to 1.5. Estimate the extrusion strain. We need to determine first the pressure applied to the end of the pellet as the ram is going to be moved forward. That means the L is going to be equal to 75 millimeters. So we're going to do the test to find the ram pressure at the pellet length of 75 millimeters, when the L is going to be dropped to 50 millimeters, when the length is going to be dropped to 25 millimeters, and when the length is going to be dropped to 0. And compute the ideal true strain. The extrusion strain using the Johnson formula and the average flow stress can be calculated as following. The strain, ideal true strain, is going to be given by as ln of the Rx. The Rx is given as 4, so the strain is going to be equal to ln of 4. The true strain is going to be given as, by using the Johnson equation, the A plus the B multiplied by the ln of the Rx. The average flow stress is going to be equal to the K multiplied by the mu up to power n and divided by 1 plus n. So far, we have all these parameters, so we can start to do the calculation. The mu is equal to ln of 4, and this will give you 1.3863. The ux is going to be equal to the A plus B multiplied by the 1.38. So we're going to have 0.8, which is the A, plus 1.5 multiplied by 1.3863. And this will give me the value to be 2.8795. Finally, for the average flow stress, we're going to multiply the K value by the value of the mu up to power n and divide by 1 plus n. And thus we're going to find that the Y prime F is going to be equal to 373 megapascal. Now we found these values and we can continue to do the calculation for the forces, for the pressure and the forces. So we can make a table and we start to do the calculation. With the die angle of 90, the billet metal is going to be assumed to be forced through the die opening almost immediately. And thus, our calculation will assume that the maximum pressure is going to be reached at the pellet length of the 75 millimeters. So we start here. Well, the L is going to be 75 millimeters. And we know the value for the DO, we calculate the mu x, and we know the value for the Y prime F. So we're going to apply the equation at different value for the L's, and we're going to find out that the value for the pressure at the length of the 75 millimeters is going to be equal to 3,312 megapascal. As the length is going to be dropped to 50 millimeters, the pressure is going to be dropped to 2,566 megapascal. When the length is going to be dropped to 25 millimeters, the pressure is going to be dropped down to 1,820 megapascal. And finally, when the length is going to be equal to 0, the pressure is going to be dropped to 1,074 megapascal. So we found the 4 pressures. And now just remember that the area is going to be the same, so we can find the force immediately. Now the effect of the die angle again. The low die angle, the surface area is going to be large, which will increase the friction at the die pellet interface. Higher friction will suddenly going to be results in the large round force. For the large die angle, more turbulence in the metal will flow during the reduction, and the turbulence will suddenly begin to increase the round force required. So once again, it's not about the lowest value for the die angle, it's not about the largest value for the die angle. We need to find the optimum value will cause the less forces to be used. So the optimum angle will depend on the work materials, the fillet temperature, and the lubrication to be applied. The shape of the extrusion die orifice, the simplest cross-section shape is going to be the circular die orifice. The shape of the die orifice will affect the round pressure, of course. More complicated shape is going to be because more forces or more pressure is going to be used. As the cross-section become more complex, a higher pressure and a greater force are going to be required. The effects of the cross-section shape or the pressure can be assessed by means of the die shape factors or the Kx. The extrusion processes are either going to be horizontal press or the vertical press. The horizontal is the most common one because we can use it for making longest part. The extrusion presses usually going to use a hydraulic uh, uh, driving machines, which is going to be especially suited for the semi-continuous direct extrusion of long sections. The mechanical drives are often going to be used for the cold extrusion of the individual parts. Now the final, actually not the final, we still have the wire drawing. The other operation of the bulk deformation processes is known as the rolling. And again, the rolling is forcing the part, which is going to have usually a flat shape, to be rolled between two rollers that are going to deform the shape to have a lower thickness section. So in the case of the rolling deformation process in which the work thickness is going to be reduced by the compressive forces exerted by the two opposing rolls, as shown below, is going to be what we know as a flat rolling. Now this is a flat rolling because we can have different shapes of the rolling are also going to be possible. So the rotating rollers are going to perform two main functions. First is going to be pulling the work into the gap between them by the friction between the work part and the rollers. At the same time, they're going to be squeezing the work to reduce its cross section. So what's happened once again? We're going to have the initial thickness, we're going to have the final thickness. Usually the final thickness is the difference between the distance between the two rollers. So as we're going to apply the force, you can see that two rollers are moving in the opposite direction. This will cause the part to be moving in between. Okay, so it's going to be pull it, and this will be happen because we're going to have friction in these two contact area. At the same time, it's going to be squeeze it and force it to be thinner from the original shape. Now, because the volume is going to be the same, just remember that the width of the parts at the exit is going to be more than the width at the part at the inlet. The types of the rolling are not just a flat rolling like what we saw earlier. Based on the workpiece geometry, we can have the flat rolling and we can have the shaped rolling. So the flat rolling is just something again to use to reduce the thickness of the rectangular cross section. While in the shape rolling, the square cross section is going to be formed into the shape such as the I-pin, as you can see here. So this is a flat rolling, and this is a shape rolling. Based on the work temperature, also can classify the rolling as the hot rolling and the cold rolling. And once again, for the case of the hot rolling, it can achieve a significant deformation. For the cold rolling, can be produced a sheet and the plate stock. Just remember once again that the hot rolling disadvantage is that it's going to increase the coefficient of friction between the work part and the roller, and thus we're going to need more forces to do the work. The rolled products made of steel can be found in these two links that are going to be supplied to you in the PDF format of this lecture slide. Now, the analysis of the operation. The first thing happening in the rolling process and can be analyzed is what we call the draft. The draft is the amount of the thickness reduction, or the original thickness of the work part minus the final thickness of the work part. The other term is the reduction. Reduction is a draft expressed as a function of the starting stock thickness. So the reduction value is going to be equal to the draft divided by the original thickness. The draft, calculate the first step, divided by the original thickness. Now, spreading, in addition to the thickness reduction, rolling usually is going to increase the work width because the volume is constant. So the original thickness multiplied by the original width multiplied by the original length is going to be equal to the final thickness multiplied by the final width multiplied by the final length. Okay, so if I know what the original thickness, what the final thickness, the final width, I can find what will be the final length of the work part. So again, to leave this analysis, again to go simply for the calculations, and again to do the calculation of the velocity, but you have to know that actually the velocity of the work part at the work part at the interest is going to be less than the final. Now what's happening is that the acceleration will be happening because the thickness is going to be less and length is going to be longer, and we're going to have higher velocity at the. So other parameter we can calculate after we calculated the reduction, after we calculated the draft, is we can calculate the strain. So the true strain can be calculated simply by using the length of the original thickness divided by the final thickness. So just remember that the original thickness is more than the final thickness, so we have length of a value more than 1. The average flow stress can be calculated by using the same equation we use for the case of the extrusion. So the y prime f, or the average flow stress, is going to be equal to the k multiplied by the true strain up to power n divided by 1 plus n. The average flow stress is going to be used to compute the estimates of the force and the power in the rolling process. The friction in the rolling occurs at a certain coefficient of friction, and the compression force of the rollers multiplied by this coefficient of friction results in the friction between the force between rollers and the work part. On the entrance side of the no-slip point, the friction force is going to be in one direction, and on the other side is going to be in the opposite direction of the work part. However, the two forces are not going to be equal, and the friction forces of the entrance side is going to be greater, so that the net forces pulls the work through the rolls. There is a limit of the maximum possible draft that can be accomplished in the flat rolling with a given coefficient of friction. And this will be defined as the following. The maximum possible draft, or the maximum thickness change we can find, is going to be equal to the coefficient of friction square multiplied by r, which is the radius of the roller. That means higher roller diameter or bigger roller can make more deformation on the work part. Coefficient of friction in the rolling depends on the lubrication, the work materials, and the working temperature. In the cold rolling, the value is going to be something about 0.1. In the warm working, typical value is going to be equal to 0.2. In the hot rolling, the value will be increased to 0.4. Hot rolling is going to be usually characterized by the condition called the sticking. So there will be sticking between the part and the rollers, in which the hot work surface is going to be adhered to the rolls over the contact arc. This condition often is going to be occurs in the rolling of the steel at high temperature alloys. When the sticking occurs, the coefficient of friction can be as high as 0.7. So just imagine how much force is going to be required to rotate the rolls during the process. So again, to leave this one, again, to go back to the equation directly, the force in the rolling can be simply approximated by using the following equation. The force is going to be equal to the average flow stress multiplied by W multiplied by the L. Now, what is the L? The L is the contact length between the roller and the part, and this will be equal to under square root of the roll radius multiplied by the draft, TO minus the TF. So we can simply calculate this value and we can find the value of the force. Now the torque required to move the rolls is going to be equal to half multiplied by the force multiplied by the L. So when you calculate the force, you calculate the L, you use it to calculate the force, then you can use it once again to calculate the torque. The power required to drive each roll is going to be the product of the torque and the angular velocity and for the pair of the rollers. So the power is going to be equal to the torque multiplied by the omega. Omega is the angular velocity. So simply the power is going to be equal to 2 multiplied by the pi multiplied by the RPM value multiplied by the F multiplied by the L. And the unit is going to be always joule over second, which is watt. Now, the final example we're going to have in today's session is about the flat rolling. So we have 300 millimeter wide strip or 25 millimeter thickness is going to be fed through a rolling mill with two powered rolls. Each has radius of 250 millimeters. So far we know the width, we know the original thickness, and we know the R value, the radius of the roll. The work thickness is going to be reduced to 22 millimeters. So we're going to take it down from 25 to 22. This is the TF. In one pass of the roll speed equal to 50 revolution per minute. This is the M. Now, the work material has a flow curve defined by the K value of 275 megapascal and the M value of 0.15. And the coefficient of friction between the rolls and the work is assumed to be equal to 0.12. So this is the coefficient of friction. Bear in mind, if the friction is going to be sufficient to permit the rolling operation to be accomplished. If so, calculate the roll force, the torque, and the power. So what we're going to do first, we're going to take the given value. So this will be the W, this will be the T out. This is the R capital, the radius. And this is the T final. And this is the N. But remember this one in minute, we need to change it into second because the power is going to be joule per second. So we need to change that later to revolution per second. Now we're given the K, we're given the N, we're given the mu value. We need to find if this friction, coefficient of friction, is going to be sufficient to permit the rolling to be accomplished. Then we need to find the value for the F, the value for the torque, and the value for the power. So just remember, the first thing we need to do is calculate the D. Calculate the D maximum. Okay, and then we're going to calculate the L. We're going to find the F. We're going to find the torque. We're going to find the power. So let's go and do the calculation. First thing we're going to do is find the value for the D. So we know this one is 25, this one is 22. So the draft is going to be equal to 3 millimeters. Now I want to find what will be the maximum draft. So just remember that the D maximum is going to be equal to the mu square multiplied by R. So mu squared divided multiplied by r. So we know the value for the mu is given, the r is given, then we can apply these values and we can find that the maximum drive is going to be equal to 3.6 millimeters. So the d maximum is more than the d value, and thus this fraction will be acceptable. Okay, so the rolling operation is going to be feasible. Now we are going to determine the rolling force. We need to find first the y prime f. W is known, we need to find the value for the L. So we start with finding the value of the L, which is going to be under square root of the radius multiplied by the d. 250 multiplied by the d of 3 millimeters under square root, and we can find the value for the L. We can find the value for the true strain, which is 25 divided by the 22 ln. We can find the value for the y prime f, and we can find the value for the force. So first we have the 250 multiplied by 3 under square root, and this will be 27.4 millimeters down. Now the length of 25 divided by the 22, and this will be 0.128 millimeters. Done. Now I'm going to apply the parameters to find the value for the y prime f, or the average force stress, and I found it to be 175.7 megapascal. Done. Now I'm going to apply the value for the f. So I'm going to have 175.7 megapascal multiplied by the width multiplied by the L. So 175 multiplied by 300 multiplied by 27.4, and this will give me that the value is going to be equal to 1,444,786 Newton. Done. Now I need to find the torque. So the torque is going to be equal to the half multiplied by the force multiplied by the length. So the 0.5 multiplied by 1,444,786 multiplied by the length of 27.4 divided by 1,000. Now why divided by 1,000? Because I need to change that into a meter from millimeters. Because the torque is going to be in Newton meters. So I'm going to get 19,786 Newton meter. Now I need to find the power. So what we can find is that the power is equal to 2 pi n multiplied by the F multiplied by the L. So of course I need to do some changes here. 2 pi 50 Newton, 50 revolution per minute, divide that by 60 to make it revolution per second. That's in Newton, and this one is going to be meter, and thus I'm going to have the answer to be equal to 207,201 Newton meter per second, which is the watt. Or I can simply change it to a horsepower, and it's going to be 278 horsepower. You don't have to do that. Newton meter is going to be Newton meter per second is going to be enough. Okay, now this is the example of the this is the example of the rolling mill for the hot flat rolling, and as you can see here that the steel plate is seen as the glowing at the lower left corner here. So the rolling mills is an equipment which is going to be massive and expensive. The rolling mill configuration can be shown in the following list of diagrams. So you can have the two heights, which is the most common one. We can have three high, which is going to have the work is going to be passed through the rolls in both directions. So 1, 2, we call it three heights because we have three rolls. We have the four heights because we're going to have the packing rolls supporting the smaller one. So the main reason for that, we're going to have higher velocity with less torque because we're going to have larger rotating the smaller one. We can have the cluster mill, 1, 2, 3, 4, 5, 6, multiple packing rolls on the smaller rolls. We have the tandem mill, tandem rolling mills. We're going to have a sequence of the two high mills. So each one is going to reduce the thickness by a certain value. The shape rolling is work deformed into a contoured cross-section rather than a flat one, accomplished by the passing of the work through rolls that have the reverse of the desired shape. And this to produce a construction shapes such as the I-beams or the L-beams and the U channels. Rolls for the railroad tracks are made by this process. Round and the square bars and rolls also can be performed by the shape rolling operation. The thread rolling is a mass production process to make the bolts and nuts. So the usually it's going to for the bolts, sorry, not the nuts. So the thread rolling is a metal rolling process used to extensively in the manufacturing industry to mass produce the screws. It's important for the mass production bolts and screws, performed as a cold working in the thread rolling machines. The advantage is the advantage over the thread cutting or the machining, high production rates, better material utilization, strong threads, and better fatigue resistance. We have also the ring rolling, which is a deformation process in which a thick-walled ring of a smaller diameter is going to be rolled into a thin-walled ring of a larger diameter. As a thick-walled ring is going to be compressed, deformed, metal will elongates, and this will causing the diameter of the part to be larger. The hot working process for the large rings and the cold working process for the smaller rings. The products will include the ball and the roller bearing races, the steel tires for the railroad wheels, and the rings for the pipes, pressure vessels, and the rotating machinery. So these are some of the examples for the rolling case. So you can see we're going to have the table shape of the roller, which is going to cause the part to be elongate and get thinner as we're going to apply the forces. So the final process we're going to cover today is going to be the wire and the bar drawing. So you can see here we are going to have the drawing instead of the extrusion. So that means that the part is going to be pulled out instead of pushed in. So in this operation, the cross-section of the bar, rod, or the wire is going to be reduced by pulling it through the die opening. Similar to the extrusion, except that the work is going to be pulled through the die in the drawing, where it's going to be pushed through the die in the extrusion. Although the drawing applied the tensile stress, a compression also is going to be plays a significant role since the metal is going to be squeezed as it's going to be passes through the die opening. Okay, so again to drag the part through the die, and thus we're going to cause the diameter to be different. The area reduction in the drawing, the change in the size of the work is going to be actually given by the area reduction. The area reduction is going to be equal to the original area minus the final area divided by the I'm sorry, there was an airplane passing by. So the change in the size of the work usually is going to be given by the area reduction. The reduction is going to be equal to the original area minus the final area divided by the original area. The R is the area reduction in the drawing, AO is the original area of the work, and the AR is the final work area. The terms of the wire drawings with the bar drawings. Difference between the bar drawings and the wire drawing is going to be the stock size. In the case of the bar drawing, we are going to use larger diameter bar and the broad stock. In the wire drawing, a small diameter stock where the wire size is going to be down to 0.03 millimeters are going to be possible. Both of the machines are going to be the same. The method, the equipment, and even the terminology is going to be different. The drawing practice and the products are the drawing practice usually going to be performed as a cold working, most frequently used for the round cross sections. The products we are going to get from the drawing practice are going to be the wire for the critical wires, torque wire for the fences, the coat hangers, and the shopping carts. The rod stock for the nails, the screws, the rivets, and the springs. The bar stock for the metal bars for the machining, forging, and the other processes. The bar drawing usually is going to be accomplished as a single draft operation. So we are then going to get the bar, passing it through one die, and we're going to change its diameter. The beginning stock has a large diameter and is a straight cylinder, requires to be a patch type operation. Unlike the bar drawing, the wire drawing is going to have a continuous drawing machines consisting of a multiple draw dies, typically something between 4 to 12, separated by an accumulating drums. Each drums, or what we call the capstans, as you can see here, capstan 1, 2, and 3, are going to provide the proper force to draw the wire stock through the upstream die. So this is die 1, die 2, so you can see that we can have diameter 1, diameter 2, diameter 3, 4, 5, and so on. Each die will provide a small reduction, so the desired total reduction is going to be achieved by the series of the dies. Annealing is sometimes going to be required between the dies to relieve the work hardening. The, the features of the draw die is similar to what we have in the case of the extrusion. Entry regions where the funnels lubricants into the die to prevent the scoring of the work and the die. We have the approach cone-shaped regions where the drawing occurs. We have the bearing surfaces where to determine the final stop size. We have the back relief exit zone provided with the back relief angle or the half angle, which is about 30 degrees. We have the dies materials, which usually again use the tool steels to or the cemented carbide materials. To prepare the materials for the drawing operation, we need to do the annealing to increase the ductility of the stock. The annealing is a very simple process. We're only going to heat up the metal to a recrystallization temperature and leave it to cool down. Usually it's going to be done by slow cooling. The cleaning to prevent the damage to the work surface and the draw die. And also we need to do the pointing, something like sharpening of the head to reduce the diameter of the starting end and allow the insertion through the draw die. So that's it for today's lecture. What I would like you to do is to focus on the examples we have because they are similar to the question we have in the assignment and also similar to the question you are going to get in the final exam. We're going to have the tutorial later and I hope we're going to have more examples that explain to you the process of the calculation we had for this topic.